Tonight, somewhere in the deep dark above you, there is a ring made of galaxies, so wide that light itself, the fastest thing there is, needs more than 1 billion years just to cross from one side of it to the other. And by the rules we have trusted for 300 years, it should not be there at all. It is too large to have formed. Too large, the equations quietly insist, to exist. And yet there it is, mapped by careful astronomers in the age of the great telescopes, in the age of James Webb. One enormous, impossible ring. And it is not the only one. Over the last decade, in the deep sky and the distant data, astronomers have kept finding things this large, shapes and structures that, by our best understanding, are simply too big to be there. And woven through the very same years, the James Webb Space Telescope has been sending back an early universe that looks too grown up and arrived too soon. Tonight, slowly and gently, we are going to look at all of it. So we are going to take something apart, very gently, not break it, just loosen it, the way you might loosen a knot you have stopped being able to feel, and look at the threads. The thing we are going to loosen is one of the oldest and quietest assumptions in all of science. It is the idea that the universe, on its largest scales, is smooth, the same everywhere, the same in every direction. No center, no edge, no special place, no preferred way to face. For 300 years, that idea has been the flaw under nearly every equation we have ever written about the cosmos. And lately, very softly, the floor has begun to creak. There is no alarm in that creaking. That is the first thing to settle into tonight. This is not a story about something being wrong. It is a story about something being larger than we expected, which is a very different feeling. When a map turns out to be too small, the land underneath it does not change. The mountains are exactly where they always were. It is only the paper that needs redrawing, so let your shoulders come down. Whatever we find tonight, the stars above your roof will still be there in the morning, in exactly the places they have always kept. Let us start with the assumption itself, because it is a beautiful one, and it is worth understanding why anyone believed it in the first place. Imagine you could zoom out, not a little. Imagine you could pull back from the Earth until the whole planet was a fleck of light, and then keep going until the sun was a fleck, and then keep going until the entire Milky Way, all 400 billion of its stars, was nothing more than a single soft smudge among countless others. From down here, the universe looks wildly uneven. There are bright places and dark places. There are stars and there are enormous gulfs of nothing between them. The sky is lumpy. It has texture, structure, drama. But the assumption says that all of that lumpiness is local. It says that if you pull back far enough, the lumps blur together. The way the individual grains of sand on a beach blur into a single smooth tan color when you look at the shoreline from an airplane. Step close, and it is all separate grains. Step back, and it is one even surface. The universe, the assumption says, is like that. Lumpy up close, smooth from far enough away. This idea has a name. It is called the cosmological principle, and it rests on two quieter ideas folded inside it. The first is homogeneity, which is just a long word for sameness from place to place. It means that one large region of the universe, averaged out, looks like any other large region. There is no richer neighborhood and no poorer one. No downtown, no suburbs, no special corner where the good stuff collected. The second idea is isotropy, which means sameness in every direction. It means that whichever way you turn to look, the universe, on average, offers you the same view. There is no up, no down, no grain to the wood, no direction the cosmos secretly prefers. homogeneity and isotropy. Same from place to place, same in every direction. Hold those two together and you have the floor we mentioned, the surface every modern equation about the universe was built to stand on. Now, where did this come from? It did not arrive all at once. It crept in slowly, the way the most powerful assumptions usually do, by being so useful that no one stopped to question it. Go back to 1687. Isaac Newton has just published his great work on gravity, and he is thinking about the stars. In Newton's picture, the universe is static. It is not expanding, it is not contracting, it simply is. An infinite and unchanging hall of stars hanging in the dark. And Newton noticed something clever about that. If the universe were finite, with an edge and a center, then gravity would eventually pull all the stars inward, collapsing them into a single heap at the middle. The only way to avoid that collapse, he reasoned, was for the universe to be infinite and evenly filled, stars scattered in every direction without end, so that every star is pulled equally on all sides, and therefore, on balance, pulled nowhere. The evenness was not yet a measurement, it was a requirement. The universe had to be smooth, or it would fall in on itself. That was the first version of the idea. A smooth universe held still by its own symmetry, and it stood, more or less unchallenged, for more than 2 centuries. Then, in the early 20th century, Albert Einstein came to the same assumption from a completely different direction. Einstein had rewritten gravity itself. In his hands, gravity was no longer a force reaching across empty space. It was the bending of space and time by the presence of mass. And when he tried to apply his new equations to the entire universe at once, he ran into a problem. The mathematics was impossibly complicated unless he could make one simplifying assumption, the same one Newton had leaned on. He assumed the universe was, on the larger scales, smooth, homogeneous and isotropic, the same everywhere, the same in every direction. With that single assumption, Einstein's equations became solvable, and what they revealed was startling. The universe described by those equations did not want to sit still. It wanted to expand. Einstein, who still believed in a static cosmos, was so unsettled by this that he added a term to his own equations specifically to hold the universe still, a fudge he would later call his greatest mistake, because within little more than a decade, the astronomers would look up and find that the universe was, in fact, expanding, exactly as the unfudged equations had quietly insisted. But notice what carried through all of it. From Newton's infinite still hall of stars, to Einstein's expanding cosmos, to every model that has come since, the smoothness survived. It was the one assumption nobody felt the need to defend, because it felt so obviously, restfully true. Of course, the universe is the same everywhere. Of course, it has no center, no special place. We learned a long time ago that the Earth is not the center of things, and it felt only natural to extend that humility all the way out, to assume that no place is the center, that everywhere is ordinary, that the cosmos plays no favorites. It is a generous idea when you sit with it. It says that wherever you happen to be, you are standing somewhere perfectly typical. Your view is everyone's view. The patch of universe over your house is, in the grand average, the same as the patch over any house anywhere, on any world, in any galaxy. There is something deeply calming in that. No one is special, which means no one is left out. The cosmos is even. The cosmos is fair. For 300 years, that assumption felt utterly safe. And for most of that time, every new thing we learned only seemed to confirm it. But to understand why the recent discoveries have made cosmologists lean forward in their chairs, you first have to understand something about how the universe builds things. Because the smoothness is not just an aesthetic preference, it comes with a rule, a speed limit, written into the structure of space itself. And that rule sets a quiet ceiling on how large anything in the universe is allowed to grow. That is where we will drift next. To understand the rule, we have to go back to the very beginning, when the universe was young and hot and very nearly, but not quite, smooth. In the first fraction of a second after the Big Bang, the universe was filled with an almost featureless soup of energy and matter. Almost featureless, but not perfectly so. There were tiny variations in density, places where the soup was a whisper thicker, and places where it was a whisper thinner. We are not talking about large differences. We are talking about variations smaller than 1 part in 100,000. If you smoothed a still pond until the deepest dip and the highest rise differed by less than the width of a single hair, you would have something like the unevenness of the early universe. Almost nothing, but not quite nothing. And not quite nothing turns out to be everything. Because gravity is patient and gravity is greedy. A region that is very slightly denser than its surroundings has very slightly more gravity, so it pulls in a little more matter from nearby, which makes it denser still, which gives it more gravity still, which pulls in more matter. Over millions and then billions of years, those faint early ripples grew, slowly, relentlessly, the rich regions getting richer, drawing material out of the thin regions, until the thin regions became the great empty voids, and the dense regions became the places where matter gathered into the first stars, then galaxies, then clusters of galaxies. This is how the universe builds things, not by placing them, but by growing them, the way frost grows on a window or a crack grows across ice, following the faint lines that were already there, and the structure it grew is genuinely beautiful. Astronomers call it the cosmic web. Galaxies are not scattered randomly through space. They are strung along immense filaments, bright threads of matter that stretch across the dark, meeting at dense knots where great clusters of galaxies gather, and surrounding vast bubbles of near emptiness called voids. From far enough away, it looks less like a scattering of dots and more like a living tissue, or the branching of neurons, or the foam left on a beach when a wave pulls back. So the universe is not perfectly smooth up close. It has this web, this lovely lacework of light and shadow. And here is where the rule comes in. Because the web took time to grow, and the growing was governed by a strict limit none of it could break. Gravity, like everything else in the universe, travels at the speed of light. When a dense region reaches out to pull in nearby matter, its influence does not arrive instantly. It spreads outward at light speed, no faster. And the universe has only existed for a finite time, about 13.8 billion years. Put those two facts together and you get a ceiling. In 13.8 billion years, gravity's influence can only have reached so far. There simply has not been enough time since the beginning for any connected structure to grow beyond a certain size. The web can be vast, but it cannot be infinitely vast. There is a largest possible thread, a longest possible filament, a biggest a single connected thing is allowed to be. Let me give you a way to hold this, because the number itself is enormous and the mind needs something to grip. Imagine the entire observable universe shrunk down to the size of a football field, end zone to end zone, the whole cosmos that we can see, scaled to that length. On that field, the largest structure the rules allow, the biggest single connected thing gravity could possibly have assembled in the time available, would be roughly the length of a single stride, a few feet of grass on a 100-yard field. Anything bigger than that one stride should not exist as a single organized structure. It should be too large to have formed. There has not been enough time since the beginning for gravity to stitch anything larger together. In real units, astronomers put a number on this ceiling. The work most often cited comes from a 2010 study by 3 researchers, Yadav, Bagla, and Kandai, who calculated, within the standard model of cosmology, the larger scale at which the universe should still look meaningfully lumpy. Beyond that scale, the lumps must average out into smoothness because nothing larger has had time to organize. Their answer came to roughly 370 megaparsecs. A megaparsec is an astronomer's unit, and 370 of them works out to about 1.2 billion light years. That is the stride on the football field. That is the ceiling. Any individual structure in the universe, any single connected arrangement of galaxies, should top out somewhere around 1.2 billion light years across. Above that, the cosmological principle insists you should find only smoothness, the lumps blurring into the even tan of the beach seen from the airplane. Now, 1.2 billion light years is already almost impossible to feel. Light is the fastest thing there is, and it would need 1.2 billion years just to cross such a structure from one side to the other. To make that gentler, hold a different comparison. The dinosaurs went extinct about 66 million years ago. That already feels like deep time, an unreachable distance into the past. Now stack that span end to end almost 20 times, and you begin to approach 1 billion years. Light crossing the largest allowed structure would have set out long before any dinosaur drew breath, long before complex life, back when the most sophisticated thing on Earth was single cells drifting in an ancient sea, and it would still be in transit today. That is the size of the ceiling, and the ceiling, the rules say, is not to be exceeded. So we have the assumption, and now we have the rule that comes with it. The universe should be smooth on the largest scales, and the largest single thing in it should be no more than about 1.2 billion light years across. This is not a wild guess. It falls directly out of the same equations that have predicted, with breathtaking accuracy, the temperature of the early universe, the amounts of hydrogen and helium it produced, and the faint glow that still fills the sky. The size limit is part of a package that has worked again and again for a very long time, which is exactly why it matters when astronomers, looking into the deep dark, began to find things that seemed to reach right past that ceiling, as if the limit were a suggestion rather than a law. We will get to those things slowly, one at a time. But first, it is worth spending a quiet moment on just how much evidence there was, for how long, that the smooth universe was real, because the assumption did not survive 3 centuries on faith alone. It survived because every time we tested it, it seemed to pass. That is the calm we will sit in next, before the gentle turn. Before we follow the astronomers into the deep dark, let us stay a while in the calm, because the smooth universe was not a careless assumption. For most of the last century, every serious attempt to test it came back with the same gentle answer. Yes, as far as we can measure, the universe really does look the same everywhere, and the same in every direction. The reassurance came from several directions at once, and the strongest of them is the glow on the screen in front of you. This is the oldest light in the universe. It is called the cosmic microwave background, and it is, in a real sense, a photograph of the cosmos as an infant. When the universe was very young, it was too hot for atoms to hold together. Electrons and nuclei flew about freely in a dense fog, and light could not travel far before scattering off a stray particle. The whole universe was opaque. a glowing fog with no clear view through it. Then, about 380,000 years after the beginning, the universe cooled just enough for electrons and nuclei to settle into stable atoms. The fog cleared, and the light that happened to be traveling at that exact moment was suddenly free to cross the universe unobstructed. That light has been traveling ever since. For 13.8 billion years, it has been crossing space, and as it traveled, the expansion of the universe stretched it, pulling its waves longer and longer until what was once a fierce glow became a faint whisper of microwaves filling every cubic centimeter of space, arriving at our instruments from every direction at once. It is everywhere. It is the afterglow of creation, and we are bathed in it constantly, a sea of ancient light we cannot see with our eyes, but can map in exquisite detail with the right machines. And here is what makes it such a comfort to anyone who loves the smooth universe. When you measure the temperature of that ancient light in one direction and then another, all the way around the sky, you find that it is almost perfectly the same everywhere. Point your instrument at one patch of sky, and the glow reads about 2.7 degrees above absolute zero. Turn to the opposite side of the sky, and it reads the same. Turn anywhere at all, and the answer barely changes. How uniform is barely. The variations from place to place are smaller than 1 part in 100,000. The whole sky glows at one even temperature, to a precision that is genuinely hard to imagine. If the surface of the ocean were as smooth as the cosmic microwave background, the largest wave anywhere on Earth would be a fraction of a millimeter high. This is the evenness the cosmological principle predicted, written across the entire sky in the oldest light there is. For decades, every time a new and more sensitive instrument went up, from the early satellites to the Great Planck mission, it returned the same answer, and each time the smoothness held, sharper and cleaner than before. The microwave background was not the only reassurance. When astronomers mapped the positions of millions of galaxies across great surveys of the sky, they saw the cosmic web in all its branching beauty, the filaments and the voids, lumpy and dramatic up close. But when they averaged it over large enough volumes, the lumpiness faded, exactly as it was supposed to, blurring toward smoothness once you step back past a certain scale. The beach, seen from the airplane, came out an even tan. And there was a third reassurance, quieter and more technical, but worth a gentle mention, because it is one of the most elegant confirmations in all of cosmology. Remember those faint ripples in the early universe, the variations smaller than 1 part in 100,000. In the hot early soup, those ripples behaved like sound waves. Pressure pushed outward against gravity pulling inward, and the result was a kind of ringing. Waves of compression spreading through the cosmos at enormous speed. When the universe cooled and the fog cleared, those sound waves froze in place, leaving a faint preferred distance between regions of higher density, a soft echo about 1 billion light-years across. Astronomers call these baryon acoustic oscillations, which is a heavy name for a tender idea, the fossilized sound of the newborn universe. And when they went looking for that frozen echo in the way galaxies are spaced across the sky, they found it, right where the equations said it should be, a gentle statistical preference for galaxies to sit about 1 billion light-years apart, the ghost of an ancient ringing. It was one more prediction of the standard model coming true, one more reason to trust the smooth universe and the rules it came with. So this is the calm we have been sitting in, a model that predicted the temperature of the sky and got it right, a model that predicted the smoothness and found it, a model that predicted the frozen sound of the early universe and heard its echo in the spacing of the galaxies. Piece after piece fit. For a long time, the cosmological principle was not just an assumption anyone could question. It was the gold standard, the thing you built on without a second thought, the floor that had never once given way. And then slowly, in the deep surveys and the distant data, astronomers began to notice things that did not want to average out. Shapes that stayed sharp no matter how far back they stepped. Structures that, by the football field rule, by the 1.2 billion light-year ceiling, simply should not have been able to grow. The first of them came not from a famous telescope or a celebrated astronomer, but from a graduate student working quietly with the light of distant quasars, following the data wherever it led. That is where the calm gives way to wonder. In 2021, at the University of Central Lancashire in the north of England, a doctoral student named Alexia Lopez was doing the kind of patient, unglamorous work that most great discoveries are actually made of. She was mapping invisible matter, not stars, not galaxies, but the faint, diffuse gas that drifts in the enormous spaces between galaxies, the material that fills the cosmic web's threads and is far too dim to photograph directly. You cannot take a picture of something that gives off almost no light. So Lopez was using a clever trick, one that turns the brightest objects in the universe into a kind of backlighting. The trick uses quasars. A quasar is the blazing core of a young galaxy, lit by a supermassive black hole feeding on everything around it, and it is among the most luminous things in all of existence, bright enough to be seen across most of the observable universe. Lopez was not interested in the quasars themselves. She was interested in what happens to their light on the long journey to us. When a quasar's light passes through a cloud of gas on its way across the cosmos, the gas absorbs certain very specific colors, leaving thin, dark gaps in the light spectrum, like tiny notches cut into a rainbow. Each kind of atom leaves its own signature of notches, a fingerprint no other element shares. The fingerprint Lopez was hunting belonged to magnesium, specifically ionized magnesium, which astronomers write as Mung-2. Wherever a quasar's light showed the telltale notches of ionized magnesium, she knew there was a cloud of gas sitting somewhere along that line of sight, a marker of matter she could not otherwise see. By gathering thousands of quasars from the Great Sloan Digital Sky Survey, each one a backlight shining through a different part of the sky, she could begin to build a map. Not of galaxies, but of the hidden gas, the faint scaffolding of the cosmic web revealed in silhouette. This is slow, careful work. You are not looking through a telescope at a beautiful nebula. You are sitting with columns of numbers, spectra, fingerprints, building a picture point by point, the way someone might reconstruct a coastline by noting where the fog lifts for a moment here, and here, and here. And as Lopez assembled her map in one particular region of the sky, a shape began to emerge from the data. A shape she had not gone looking for. A shape that did not belong. It was an arc, an enormous, gentle curve of magnesium markers, gas clouds, and the galaxies that hold them, sweeping across the sky in a smooth crescent. And when she measured it, the size did not make sense. The arc stretched about 3.3 billion light years from end to end. Sit with that number for a moment gently, because it runs straight into the rule we spent the last section building. The ceiling, remember, was about 1.2 billion light years. That was the largest a single structure should be able to grow in the entire age of the universe. And here was a curve of matter nearly 3 times longer than that. On the football field, where the size limit was a single stride, This arc would stretch across most of the field. It was not a little over the limit. It was vastly, almost serenely over it, as if the limit had never applied. To help hold its scale in the sky, picture this. The full moon, as seen from your backyard, covers about half a degree of sky, a small disk you could blot out with the tip of your little finger held at arm's length. The giant arc stretches across roughly 20 degrees of sky. That is about 40 full moons laid side by side in a single curve, a structure so wide that if your eyes could see it directly, it would arch across a sizable fraction of the night, a vast and quiet crescent you would never be able to take in with a single glance. And it was far away. The light Lopez was reading had left the arc about 9.2 billion years ago, which means we see it not as it is now, but as it was when the universe was less than half its present age. The arc is a message from deep in cosmic time, and the message is simply this: I am here and I am too big. Now here is the part that tells you something about how good science actually works, and why this story is so easy to trust. Lopez did not announce that she had broken the universe. The reaction, hers and her colleagues, was careful, measured, almost cautious. The first question any honest researcher asks when a shape appears in the data is not, is this real, but could this be a trick of the eye? Human beings are pattern-finding creatures. We see faces in clouds and animals in the stars. Give us a random scatter of points, and we will find shapes in it, arcs and rings and lines that mean nothing at all. So the real work was not finding the arc. It was testing whether the arc could be an accident. Lopez and her supervisor, the astronomer Roger Clowes, ran the tests. They took their real map and compared it against many simulated maps in which the same number of points were scattered at random, with no real structure at all. And they asked how often a curve as long and as coherent as the giant arc would show up by pure chance. The answer was reassuring in one sense and unsettling in another. The odds of the arc being a random fluke came out at roughly 1 in 100,000. 1 in 100,000 is not certainty. Science is careful with the word certainty, and we will spend real time later on exactly what these odds do and do not mean. But it is small enough that you cannot easily wave the arc away. It is small enough that the careful thing to do is not to dismiss it, and not to panic, but to write it down and watch and wait to see whether anything else turns up. Because one strange shape in one patch of sky is a curiosity. It might be a fluke that beat the odds. It happens. The universe is large, and rare things by definition do occasionally occur. So the field did the patient thing. It noted the giant arc, acknowledged that it sat uncomfortably above the size limit, and held the question open. Lopez herself was honest about it in interviews afterward. She could not explain it, and she said so plainly, without embarrassment, because not being able to explain something is not a failure in science. It is the most interesting place you can possibly stand. It is the edge of the map, where the known runs out and the worth looking into begins. This was the first of the structures that would not average out. One quiet arc, found by a graduate student following the data, too large for the rules, sitting at the edge of explanation. If the story had ended there, it would be a footnote, an oddity, a single point that beat 1 in 100,000 odds, the kind of thing the universe occasionally tosses up just to keep us humble. But the story did not end there, because 2 years later, Alexia Lopez looked at the same patch of sky again, and she found a second shape. This one was not an arc, this one was a ring. In January 2024, at the 243rd meeting of the American Astronomical Society, Alexia Lopez stood up and announced what she had found in that same region of the sky. Not another arc this time. A ring, an immense, nearly closed circle of galaxies and gas, traced once again through the magnesium fingerprints in quasar light. She called it, simply, the Big Ring. And like the arc before it, the first thing anyone noticed was the size. The Big Ring is about 1.3 billion light-years across. Its circumference, the distance all the way around it, is roughly 4 billion light-years. Once again, we are past the ceiling. The diameter alone edges over the 1.2 billion light-year size limit, and the full loop of it, the entire circle, is a structure far larger than anything the rules say should be able to hold together as a single shape. If you could stand back and see it whole, it would be a ring of galaxies so wide that light itself takes well over 1 billion years simply to cross from one edge to the other. And here is a detail that makes it feel almost personal. The Big Ring sits in the same part of the sky as the giant arc, the same neighborhood, the same era of cosmic time. Two structures, both far too large, both found by the same person, both in the same patch of the deep universe. We will spend the next section sitting with that coincidence, because it turns out to matter. But first, let us understand what makes the Big Ring so difficult to explain away, even more difficult than the arc. Two things. The first is how confident the measurement is, and the second is its shape, which is stranger and more beautiful than a flat ring. Start with the confidence. When scientists find a pattern in noisy data, they need a way to say how seriously to take it, how unlikely it is to be a fluke. The tool they use is called sigma, and it is worth understanding gently, because it will come up again. And it is one of the most useful ideas in all of science for telling the difference between a real signal and a trick of chance. Imagine flipping a coin. Flip it 10 times and getting 7 heads would not surprise you. That happens all the time. But flip it 100 times and get 90 heads, and you would start to suspect the coin is weighted, because a fair coin almost never does that. Sigma is a way of counting how far out toward the unlikely edge a result sits. 1 sigma is common, the kind of thing that happens by chance all the time. 3 sigma is unusual, worth a raised eyebrow. And 5 sigma is the gold standard physicists demand before they will say they have genuinely discovered something new. 5 sigma means the odds of the result being a random fluke are smaller than about 1 in 3.5 million. To put that threshold in context, 5 sigma is the same level of confidence that physicists insisted on before they would announce the discovery of the Higgs boson, the famous particle found at the Large Hadron Collider in 2012. They had hints for years, but they would not say the word discovery until the signal reached 5 sigma. That is how high the bar is. That is how cautious good science chooses to be. The Big Ring reaches a statistical significance of about 5.2 sigma. It clears the bar. By the same standard used to confirm the Higgs boson, the Big Ring is, statistically, a real structure and not a chance arrangement of dots. That does not mean we understand it. It means it is very, very unlikely to be nothing. The shape in the data is almost certainly a shape in the universe. Now the second thing, the part that closed the most comfortable escape route. When the Big Ring first appeared, there was a natural, reassuring explanation waiting in the wings, and its name was already familiar to us. Baryon acoustic oscillations. Remember the frozen sound waves from the early universe? The faint ringing that left a preferred scale of about 1 billion light years and arranged some galaxies into soft, spherical shells. A ring of galaxies 1 billion or so light years across is exactly the kind of thing that frozen echo can produce. So the hopeful thought was simple. Perhaps the big ring is just one of those acoustic shells seen edge-on, a perfectly ordinary fossil of the early universe's ringing, no new physics required. It was a good idea. It would have been a gentle landing. But when Lopez and Klaus looked closely at the three-dimensional structure of the big ring, the explanation did not fit. A baryon acoustic shell is a sphere, and a sphere seen edge-on looks like a flat ring. The big ring is not flat. In 3 dimensions, it is shaped more like a coil, a corkscrew, a helix wound through space, and it is too large. Acoustic shells come in at about 1 billion light-years across, set by that frozen sound. The big ring is 1.3 billion light-years across and shaped like a spiral, not a shell. The numbers do not match, and the geometry does not match. The comfortable explanation simply does not hold, so we are left with a structure that clears the discovery threshold, exceeds the size limit, sits in the same patch of sky as another oversized structure, and is shaped like a coil that no familiar process is known to produce. Lopez again was careful. She did not claim to have overturned cosmology. She described what she had found, laid out why the easy explanations did not work, and left the harder question open and honest. In her own words to the public, neither of these two ultra-large structures is easy to explain in our current understanding of the universe. And that, once more, is not a complaint. It is an invitation. It is worth pausing here to notice how different this feels from the way these stories are often told. There is no villain. Nothing is being attacked. A careful student found a shape, tested it against the gold standard, ruled out the easy answer, and said honestly that she could not yet explain it. That is the whole drama, and it is a quiet one. The universe handed us a coil of galaxies too large to understand, and the only correct response is curiosity. But Lopez had also noticed the coincidence we set aside a moment ago. 2 structures, same patch of sky, same distance, same era. And she began to wonder whether the arc and the ring might not be 2 separate puzzles at all, but 2 pieces of something single and larger, parts of one enormous thing reaching across that region of the deep universe. That wondering would lead, 2 years later, to one more discovery, and to a test run on one of the most powerful simulations of the cosmos ever built. So that is the next place we drift. Let us begin this section with the coincidence, because it is the thing that keeps the whole question honest. The giant arc and the big ring sit remarkably close together. They are at nearly the same distance from us, the same era of cosmic time, a redshift of about 0.8 in the astronomers' shorthand. And they are separated by only about 12 degrees on the sky, which, on the scale of the whole heavens, is the width of a few fists held at arm's length. 2 structures, both too large for the rules, in the same neighborhood, at the same depth. Lopez herself raised the possibility, gently, that they might be related, perhaps 2 parts of a single larger system that we are seeing in pieces. That idea was developed further. In a 2026 preprint, Lopez and Roger Klaus proposed a structure they called the giant ring on the sky, connecting the arc and the ring through a filament of matter, a kind of bridge, traced with a detection method named the Fill Finder algorithm. The picture they sketched was of a single immense system, the 2 oversized shapes joined into something even larger. It is a preprint, which means it has been shared with the field, but has not yet completed the full process of peer review, the careful checking by other experts that turns a claim into accepted science. So we hold it lightly, as the authors themselves do, but it deepens the puzzle. If the arc and the ring are one thing, then the one thing is bigger still. Now, This is exactly the moment where good science turns and argues with itself, and it is the most important part of tonight's story. So let us slow down and give the skeptics their full and fair hearing, because they have a real point and an honest one, and the strength of the whole picture depends on how it survives them. We touched on this earlier with the giant arc, the human tendency to find patterns in randomness. The skeptics take that worry and make it rigorous. In 2025, a group of researchers led by Til Sawala published an analysis with a title that says exactly where they stand. Gigaparsec structures, they argued, are nowhere to be seen in the standard model when you look properly. Their concern was not with the data Lopez collected, which nobody disputes. Their concern was with the method used to find shapes in that data, and whether those methods can fool you. Here is the heart of their argument, told gently. To find a structure like the arc or the ring, you run an algorithm over your map of points, a procedure that looks for groups of galaxies that seem to belong together. These algorithms have names like friends of friends and minimal spanning tree, and they work roughly by connecting each point to its nearest neighbors and seeing what shapes emerge from the web of connections. They are good tools, but the skeptics asked a sharp question. What happens if you run those same tools on pure noise? On a map of points scattered completely at random, with no real structure at all, the kind of smooth universe the standard model predicts? Do giant arcs and rings appear anyway, just from chance? To test it, Sawala and his colleagues turned to one of the largest cosmological simulations ever built, a model called Flamingo. They used a version run inside an enormous simulated volume, a cube of virtual universe measuring 2.83 gigaparsecs on a side, which is billions of light years across, large enough to contain many structures the size of the giant arc with room to spare. This is a universe built entirely from the standard rules, smooth on large scales, obeying the cosmological principle and its size limit. If you run the structure-finding algorithms inside this rule-abiding simulated cosmos, and giant arcs and rings show up anyway, then the structures Lopez found might not be violations of anything. They might just be the shapes the eye and the algorithm assemble out of ordinary randomness. And their finding was that, yes, with certain methods, arc-like and ring-like patterns of the right size can appear in a smooth, rule-following universe more often than you might expect. From this, they concluded that the giant arc and the big ring may not require any new physics at all. They may be, in the skeptic's framing, the cosmic equivalent of seeing a face in the clouds, real points arranged into a shape that our pattern-hungry minds and our pattern-hungry algorithms find compelling, but that carries no deeper meaning. This is a serious objection, and the honest thing is to say so plainly. It is exactly the kind of challenge that should be made, and exactly the kind of challenge that makes the eventual answer trustworthy, whichever way it falls. If a relaxed standard universe can grow these shapes by chance, then much of the mystery softens. But Lopez and her colleagues had a reply, and it is worth hearing with the same fairness. Their counter-analysis made several points. First, the structures they found are not loose, low-confidence smudges. The big ring, as we saw, reaches 5.2 sigma against random models, the same gold standard used for the Higgs boson. And that significance was measured precisely against the kind of random scatter the skeptics are invoking. Second, the specific three-dimensional shape matters. A corkscrew is a much more particular thing than a vague blob, and it is harder to produce by accident than a rough arc. Third, and most pointedly, when their team looked for structures of this exact size and coherence inside the rule-following simulations, the best computer-built universes did not readily reproduce the giant ring on the sky. the simulated cosmos, run honestly, simply did not grow this particular shape. So we have two careful groups of scientists looking at the same data, reaching different conclusions. And that is not a problem with the science, that is the science. One side says these shapes can be conjured from randomness if you are not careful. The other side says these particular shapes, at this size, with this confidence and this geometry, resist being conjured. The disagreement is not yet settled, and it will not be settled tonight. And there is something restful in admitting that. We are watching a genuine question being worked out in real time, by people doing their honest best, with no one cheating and no one shouting. What we can say is this: if the structures were single and isolated, the skeptic's case would be stronger. One arc that beat 1 in 100,000 odds is the kind of fluke a large universe occasionally produces. But the picture does not stay isolated, because the arc and the ring are not the only oversized things anyone has found. There is another, discovered years earlier, by a completely different method, using not the absorption fingerprints of distant gas, but the brightest explosions in the entire universe, the deaths of giant stars, used as lighthouses to map a wall so large it makes the big ring look modest. And that is where we wander next. The structures we have looked at so far were mapped through gas, through the faint magnesium fingerprints in quasar light. The one we are about to meet was mapped a different way entirely, through death, through the most violent and luminous explosions the universe is capable of producing. To map it, astronomers used dying stars as lighthouses. When a star far more massive than our Sun reaches the end of its life and collapses, it can release in a few seconds more energy than our Sun will radiate in its entire 10 billion year lifetime. The blast focuses into narrow beams of the highest energy light there is, gamma rays, and if one of those beams happens to point toward Earth, our detectors catch a flash that can briefly outshine the rest of the universe combined. We call these gamma ray bursts, and they are, for a moment, the brightest things in all of creation. Because they are so bright, gamma ray bursts can be seen across almost unimaginable distances, far beyond where ordinary galaxies fade from view. And because each burst marks the death of a massive star, and massive stars live and die where matter has gathered, each burst is also a flag planted in the cosmic web, a marker saying here, in this distant place, there is structure, there are galaxies, there is something. Map enough of these flags, and you begin to see where matter clusters across truly enormous reaches of space. In 2014, 3 researchers, Istvan Horvath, John Hakila, and Zsolt Bagoli, were studying the distribution of these bursts, looking at where they fell across the sky and at what distances. And in one region, they found that the bursts were not spread evenly. They were clustered, gathered together into a concentration far denser than the surrounding space, stretched across a region so large it is difficult to write down without the number losing all meaning. They named it the Hercules Corona Borealis Great Wall, after the constellations it lies behind. The Great Wall, by their estimate, stretched as much as 10 billion light-years across. Let that size settle, slowly, because it asks even more of us than the structures before it. The size limit, the ceiling, was about 1.2 billion light-years. The giant arc was 3.3 billion. The Big Ring, 1.3 billion across. The Great Wall is estimated at around 10 billion light-years, which is a sizable fraction of the entire observable universe. The observable universe, the whole sphere of everything we could in principle see, is about 93 billion light-years across. A single structure 10 billion light-years long would span more than 1/10 of all that we can observe. On the football field, where the size limit was 1 stride, this wall would stretch from one end zone almost to the other. And the story did not stand still. In 2025, an updated analysis revisited the Great Wall with far more data than was available in 2014. The original work rested on a couple of hundred gamma-ray bursts. The update drew on 542 of them, more than twice as many flags planted across the deep universe. And the larger dataset did not make the wall go away. If anything, the signal held, and some estimates of its span grew, with the structure possibly reaching even larger than the original figure across a great range of cosmic distance. More data, more flags, and the wall remained. That is an important kind of result, and we will come back to why in a moment. But first, in the spirit of the honest conversation we had in the last section, let us give the doubts their fair hearing here too, because gamma-ray bursts as mapmakers come with real questions attached. The concern is this: gamma-ray bursts are rare and they are scattered, and we do not always know their distances precisely. Mapping a structure from them is like trying to map a coastline from a scattering of lighthouses glimpsed through fog, when you are not entirely sure how far away each lighthouse is. Some researchers have argued that the apparent clustering of bursts in the Great Wall region might be partly an artifact, an effect of where our detectors happen to look most often, and how completely we have surveyed different parts of the sky, rather than a true concentration of matter. It is the same careful worry as before. Is this a structure? Or is this the pattern our methods impose on incomplete data? There is also a deeper statistical subtlety worth naming gently. There is a difference between a structure, meaning galaxies physically connected and held together by gravity into a single thing, and a statistical clustering, meaning simply more dots in one region than another, without those dots necessarily being bound to one another. A wall traced by gamma-ray bursts is more naturally the second kind, an overdensity, a place where matter is thicker rather than a single rigid object. And that distinction matters for the size limit. The ceiling we discussed applies most strictly to bound structures stitched together by gravity. An overdensity, a region that is merely thicker than average, is a slightly different thing. So part of the ongoing conversation is about exactly what kind of largeness the Great Wall represents. These are fair points, every one of them. And yet, here is the quiet reason the Great Wall keeps the field's attention rather than being set aside. When the 2014 result rested on a couple of hundred bursts, a skeptic could reasonably say the sample was too small, the fog too thick, the lighthouses too few. But the 2025 update more than doubled the bursts, and the signal did not fade. In statistics, the usual sign of a fluke is that it weakens as you gather more data, the way a face in the clouds dissolves the longer you stare. The usual sign of something real is that it sharpens. The Great Wall, given more than twice the data, sharpened rather than dissolved. That does not prove it is a bound structure exceeding the size limit, but it is the behavior of a signal that is trying to tell you something true. So now we have 3 of them, found by 2 completely different methods: the giant arc and the big ring, traced through the magnesium fingerprints in quasar light, and the Hercules Corona Borealis Great Wall, traced through the deaths of giant stars. 3 oversized things in different parts of the sky at different distances, found by different teams using different tools. That is the second of our structures behind us, and the third, and they are not going to be the last. The accumulation is beginning, and we will keep a soft count as we go. But notice what all 3 have in common beyond their size. They are all about the architecture of the universe, the way matter is arranged across space, we have not yet brought in the telescope from the title of tonight's story. James Webb did not map any of these three structures. Its contribution is different, and in some ways even stranger. Webb did not look at how matter is arranged across space. It looked at how matter came together across time. And what it found, when it turned its golden eye on the earliest universe, was a different kind of too much. Too many galaxies, too grown up, too soon. That is the next movement, and the next place we drift. On Christmas morning in 2021, a rocket lifted off from the coast of South America, carrying the most ambitious telescope ever built. The James Webb Space Telescope had been decades in the making, billions of dollars in the building, and it was so delicate and so complex that hundreds of separate steps all had to unfold perfectly after launch, with no possibility of repair, before it could see anything at all. Its mirror, a honeycomb of 18 gold-coated segments, was too large to fit inside the rocket and had to be folded up like origami, then unfolded in the dark after launch. Its sun shield, the size of a tennis court, had to be tensioned layer by layer to keep the instrument colder than almost anywhere in the solar system. And then it traveled, not into orbit around the Earth, like Hubble, but out to a special point in space about 1 million miles away, 4 times farther than the Moon, a quiet gravitational balance point where it could sit in permanent cold and stare into the deep universe without the Earth getting in the way. It takes a particular kind of patience to send something that far, knowing that if anything goes wrong, no one will ever reach it to fix it. But nothing went wrong. The mirror unfolded, the shield deployed, the instrument cooled, and in the summer of 2022, the first images came home. Webb was built to see further back in time than any instrument before it, and to understand why, you have to remember the gentle truth at the heart of all astronomy. When you look out into space, you are looking back into time. Light travels fast, but not infinitely fast. So the further away a thing is, the longer its light has taken to reach you, and the further into the past you are seeing. Look at the sun, and you see it as it was 8 minutes ago. Look at the nearest star, and you see 4 years into the past. Look deep enough, with an instrument powerful enough, and you can see galaxies as they were more than 13 billion years ago, when the universe was young. Webb's special gift is that it sees in infrared light. As the universe expands, the light from the most distant galaxies gets stretched. Its waves pulled longer, shifted out of the visible range and into the infrared. This stretching is called redshift, and the more distant and ancient a galaxy is, the more its light is redshifted. Webb was designed precisely to catch that stretched, ancient infrared glow, the light of the very first galaxies, redshifted by its billions of years of travel into a range Hubble could barely perceive. Astronomers measure this with a number they simply call Z. A higher Z means more redshift, more distance, more time looking back. A galaxy at redshift 7 is seen as it was when the universe was less than 1 billion years old. At redshift 10 or 12, we are looking back to within a few 100 million years of the beginning. So Webb opened its eye on the earliest universe, the era astronomers had longed to see, expecting to find the first faint, small, fragile galaxies just beginning to assemble. The standard picture said the early universe should be a nursery, full of tiny, dim, half-formed things. Galaxies were supposed to start small and grow slowly, building themselves up over billions of years by merging together, like snowballs growing as they roll. At redshift 10, less than 500 million years after the beginning, you expected scattered infant galaxies, faint and modest. That is not quite what Webb found. Almost immediately, in its earliest deep observations, the telescope began turning up galaxies that were too much, too bright, too massive, too numerous for how early they were. Galaxies at redshift 10 and even above 12 that looked far more developed than the timeline allowed, holding more stars and more mass than 500 million years of cosmic history should have been able to assemble. It was as if you had looked into a nursery expecting newborns and found, here and there, children already walking and talking. The fullest picture of this came from a great survey called Cosmos Webb, one of the largest projects Webb has undertaken, led by the astronomer Caitlin Casey and her colleagues. They pointed Webb at a single carefully chosen patch of sky and stared for 255 hours, gathering the faint light of the deep universe across an area about the size, on the sky, of 3 full moons. And in that one patch, they catalogued nearly 800,000 galaxies, reaching back across almost the entire history of the cosmos. What the Cosmos Webb map showed, among many things, was that the early universe held something like 10 times more luminous galaxies than the standard models had predicted, 10 times more bright, mature galaxies in the first chapter of cosmic history than the equations said should be there. And the survey also revealed supermassive black holes in the early universe, some of them feeding and glowing, that had been entirely invisible to Hubble. Monsters already grown large when the universe was very young. Now, the careful conversation matters here just as much as it did with the Arc and the Ring, and Webb's astronomers have been admirably honest about it. When you measure a very distant galaxy, estimating its mass and its brightness is genuinely hard. Some of the earliest, most startling mass estimates were later revised downward, as the calibrations of the new instrument were refined, and as astronomers learned that some of the apparent brightness came from feeding black holes, rather than from vast populations of stars. A few of the most extreme early claims softened under scrutiny, exactly as they should. This is not a field that has lost its head. It has checked and rechecked and lowered some of its own numbers. And yet, after all the careful revising, a real tension survives. Even with the conservative numbers, the early universe that Webb shows us is more developed, more populated with bright and massive galaxies than the standard timeline comfortably predicts. The puzzle did not evaporate under scrutiny. It got smaller and more solid and harder to dismiss. The early universe simply grew up faster than the model expected. This is a different kind of strangeness from the oversized structures. The arc, the ring, and the wall were about space, about how matter is arranged across enormous distances. Webb's early galaxies are about time, about how quickly the universe assembled its furniture after the lights came on. But notice that both strangenesses point in the same direction, toward a universe that is a little more structured, a little more grown, a little less smooth and slow than the model at its center assumed. Two different threads, pulling gently at the same loosening seam. And within Webb's crowded early universe, there are individual galaxies so striking that they deserve to be met one at a time. The first is a galaxy that should not have been able to assemble itself so soon, a great spinning disk, fully formed, seen when the universe was barely out of its infancy. Astronomers found it almost by accident, hiding in the background of an image taken for another purpose entirely. They call it the Big Wheel. That is the next place we let our attention settle. Some discoveries are hunted for years. Others simply appear in the corner of an image taken for some other reason, waiting to be noticed. The Big Wheel was the second kind. Astronomers were using Webb to study a distant quasar, a bright galactic core, when they noticed something in the background of the same frame, a galaxy that had nothing to do with what they were looking for. It was a spiral, a great, well-defined spinning disk with arms. And when they worked out how far away it was, the discovery became something far more interesting than an accident. The big wheel lies about 11.7 billion light-years away, which means we see it as it was roughly 2 billion years after the Big Bang. The universe at that point was very young, barely out of its first chapter. And yet, here was a fully formed spiral galaxy, with structured sweeping arms, looking very much like the grand, mature galaxies we see nearby in the present-day universe. To find such a thing so early is, in the gentlest possible terms, surprising. To feel why, we need to talk about how galaxies like ours are supposed to come together and how long it is supposed to take. Our own Milky Way is a spiral galaxy, about 100,000 light-years across, holding somewhere between 100 and 400 billion stars, with a central black hole about 4 million times the mass of the Sun. And the Milky Way took its time. The standard picture of how a galaxy like ours forms is slow and violent. You start with small clumps of gas and stars, and over billions of years they fall together, merge, collide, tear at one another, and gradually settle. A galaxy is built by accumulation, by countless mergers spread across most of the age of the universe. Our Milky Way took something like 13 billion years to assemble itself into the calm spiral it is today. So a fully formed spiral disk, complete with arms, seen just 2 billion years after the beginning, is a galaxy that assembled itself in a fraction of the time the Milky Way needed. It is, to borrow a comparison, like reaching into rock from the age of the dinosaurs and pulling out a finely made pocket watch, an object so intricate and so finished that it seems impossible it could already exist in that ancient layer. The big wheel is too complete for its time. And it is not only the spiral arms. There are two deeper details that make the big wheel genuinely puzzling, rather than merely early, and both are worth meeting slowly. The first is its mass. The big wheel holds roughly 5 times the mass of the Milky Way. It is not a small, fragile early galaxy that happens to have a bit of structure. It is a giant, larger than our own fully grown galaxy, and it reached that size in a small fraction of cosmic history. The second detail is the way it moves, and this is the one that astronomers find hardest to explain. When astronomers measure how a galaxy spins, they look at how fast the stars and gas orbit at different distances from the center. In a mature, settled galaxy like the Milky Way, the outer parts orbit at almost the same speed as the inner parts, producing what is called a flat rotation curve. This flatness is one of the great clues to the existence of dark matter, the invisible material whose gravity holds galaxies together. A flat rotation curve is the signature of a galaxy that has a substantial, well-organized halo of dark matter around it. A galaxy that has had time to settle into a stable, balanced spin. The big wheel has a flat rotation curve. 2 billion years after the Big Bang, it is already spinning the way a mature, fully assembled galaxy spins, with the smooth, organized motion of something that has settled into balance. Wrapped in a built-up halo of dark matter, there is a relationship astronomers use called the Tully-Fisher relation that connects how fast a galaxy rotates to how much mass it contains, and mature galaxies fall neatly along it. The big wheel falls neatly along it too, sitting right where a grown-up galaxy should, despite being seen in an era when galaxies were supposed to still be chaotic, clumpy, and unsettled. This is the heart of the puzzle. It is not just that the big wheel looks like a spiral. It is that it behaves like a galaxy that has already lived most of its life. that has already done the slow work of settling and organizing in an era when, by the standard timeline, that work should barely have begun. The slow, merger-driven story of galaxy formation does not easily produce a calm, massive, flat-spinning spiral this soon. Something allowed it to come together fast and in good order, and we are not yet sure what. Now, the same honesty we have practiced all along applies here. The big wheel is a single galaxy. One object, however striking, is not by itself a verdict on how galaxies form. It is possible that the early universe occasionally produced such things under special conditions we do not yet understand. Rare cases where matter gathered unusually fast in an unusually dense region. It is possible that as Webb finds more early galaxies, the big wheel will turn out to be one of a small family of fast-forming giants, each one teaching us something about the conditions of that era. The discovery does not overturn anything on its own. It widens the question, but place it next to everything else, and the pattern of tonight's story holds. The early universe that Webb is showing us is more grown up, more quickly assembled, more massive and mature in its first chapters than the model at the center of cosmology expected. The big wheel is the single clearest portrait of that surprise, a finished galaxy in an unfinished era, spinning calmly where there should have been only chaos. And there is one more early universe discovery to meet before we leave this movement, and it reaches even further back, to the most distant confirmed galaxy yet found. This one is not about shape or size or spin. It is about chemistry, about finding, in a galaxy seen less than 300 million years after the beginning, the chemical signature of elements that should have needed many generations of stars to forge. And it carries a lovely surprise, a thread that connects the most distant galaxy in the universe to certain quiet, ancient stars hiding in our own Milky Way, close enough to feel like neighbors. So that is where we drift now, gently. We come now to the most distant confirmed galaxy yet found, and to a name that sounds more like a code than a place, because that is what it is. Astronomers call it MOM-Z14. The letters and the number are a kind of address, and the part that matters is the Z, the redshift. MOM-Z14 sits at a redshift of 14.44, which is, at the time of tonight's story, the highest confirmed redshift of any galaxy ever measured. A redshift of 14.44 means we are seeing this galaxy as it was about 280 million years after the Big Bang. The universe then was an infant, barely 2% of its present age. If you compressed all of cosmic history into a single year, with the Big Bang on the 2nd of January and the present moment at midnight on the last day of December, MOM-Z14 would be light that left in the first few days of that cosmic January, before almost anything we know had happened. This is very nearly the beginning. The word confirmed deserves a moment, because it is what makes this special rather than merely promising. Finding a candidate for a very distant galaxy is one thing. You take an image, you see a faint red dot, and its color suggests it might be enormously far away. But color alone can fool you. Some nearby dusty reddish galaxies can masquerade as distant ones. To confirm a galaxy's distance, you need its spectrum, the light spread out into its component colors, so you can read the precise fingerprints of its atoms and measure exactly how much they have been stretched. Webb did this for MOM-Z14, taking not just a picture but a spectrum, and the spectrum confirmed the staggering distance. This is not a guess, it is a measurement, and it is a small thing, in size. Its effective radius is only about 240 light years, which by galactic standards is tiny, a compact knot of light near the dawn of everything. But its size is not what made astronomers lean in. What made them lean in was its chemistry. When they read the spectrum of MUMS-14, they found a signal of nitrogen. And nitrogen, in a galaxy this early, is a genuine puzzle because of how nitrogen gets made in the first place. Let us go slowly here, because this is one of the loveliest ideas in all of astronomy. In the beginning, the universe contained almost nothing but the lightest elements, hydrogen and helium, with a faint trace of lithium. That is all the Big Bang itself produced. Every heavier element, all the carbon and oxygen and nitrogen and iron, everything that makes up planets and oceans and the cells of your body, was forged later, inside stars. Stars are the foundries of the universe. They fuse light elements into heavier ones in their cores, and when they die, they scatter those new elements into space, where the next generation of stars and planets can gather them up. The iron in your blood, the calcium in your bones, the oxygen you are breathing right now, all of it was made inside stars that lived and died before the sun was born. Nitrogen, specifically, tends to take time. It is generally built up over multiple generations of stars as material is processed, scattered, gathered again, and processed once more. To find a strong nitrogen signal, you usually expect a galaxy that has already lived through several cycles of star birth and star death, enriching its gas step by step. So finding richly enriched nitrogen in a galaxy seen just 280 million years after the beginning is like finding a young forest that somehow already has deep, layered soil. The soil of a forest takes many seasons of growth and decay to build. To find it thick and rich in a forest that has barely sprouted is a quiet surprise. So how does an infant galaxy already have such enriched chemistry? One leading idea points to a kind of star that no longer exists anywhere in the universe today, the very first stars of all, which astronomers call population 3 stars. These were the first generation, formed from the pure hydrogen and helium of the early cosmos, with none of the heavier elements that later stars inherit. And because they formed from such pristine material, they are thought to have been monsters, vastly more massive than the Sun, blazing fiercely and dying young, perhaps within only a few million years. A star like that lives fast and dies hard, and in its brief, violent life and death, it can forge and scatter heavy elements quickly, seeding its surroundings with enriched material far faster than ordinary slower stars. A first generation of these giants could, in principle, salt an early galaxy with nitrogen and other elements long before the slow, normal enrichment would have managed it. We have never directly seen a population 3 star. They are theoretical, inferred from the physics of the early universe rather than observed. But their fingerprints may be exactly what galaxies like MUMS-14 are showing us. The chemical aftermath of a first generation of giants that lived and died before the galaxy was 300 million years old. And here is the thread that makes this so quietly beautiful, the part that reaches all the way back home. We do not only see these strange early chemical patterns in the most distant galaxies, we also see echoes of them much closer, in our own Milky Way. Scattered through our galaxy are certain very old, very metal-poor stars, ancient survivors that formed long ago from gas that had been enriched by only the earliest generations of stars. And some of these old local stars show unusual nitrogen patterns, chemical signatures that resemble what we are now seeing in galaxies near the dawn of time. The early universe, it turns out, left its fingerprints everywhere, including in stars quietly orbiting within our own galaxy, close enough that their light reaches us in mere thousands of years rather than billions. There is something restful in that connection. The most distant galaxy we have ever confirmed, seen almost at the beginning of everything, is telling us about a process whose echoes are written into stars we could point a backyard telescope toward. The universe is enormous and strange and old beyond comprehension, and yet its story is continuous, its early chapters still legible in the chemistry of things close to home. So that is Webb's contribution to tonight's story. Not the giant structures of arc and ring and wall, but the early universe itself, grown up too fast, too richly populated, too chemically mature, too soon. Two threads, the great structures and the early galaxies, both pulling gently at the same assumption of a smooth, slow, even cosmos. But there are two more strains showing up, from completely different directions, and they have nothing to do with size or with early galaxies. They have to do with how fast the universe is expanding, and with whether it has, against all the rules, a preferred direction. Two careful measurements that will not agree, and a possible arrow in a cosmos that is supposed to have none. That is the next movement, and the next place tonight will take us. Let us open this one with a person and a sentence rather than with a number. A few years ago, an astronomer named Dan Skolnick, who has spent his career carefully measuring how fast the universe is expanding, said something that quietly got the attention of his whole field. He said that the disagreement his measurements kept revealing was no longer just a tension. It was, in his words, turning into a crisis. Coming from a careful scientist who chooses words precisely and does not reach for drama, that was a striking thing to say. And what he was talking about was, on its surface, very simple. Two ways of measuring the same number keep giving two different answers, and the gap between them refuses to close. The number they are measuring is called the Hubble constant, and it is one of the most important numbers in all of cosmology. It describes how fast the universe is expanding, how quickly distant galaxies are receding from us as space itself stretches. Nearly a century ago, the astronomer Edwin Hubble discovered that the universe is expanding at all, that distant galaxies are moving away, and the farther away they are, the faster they recede. The Hubble constant is the precise rate of that expansion, the speed of the stretching. Pin it down accurately, and you can calculate the age of the universe, its size, and its future. It is a cornerstone number, and for decades the great project was simply to measure it more and more precisely. The trouble is that there are two very different ways to measure it, and they have become precise enough to clearly disagree. Let us walk through both slowly, because the disagreement only becomes meaningful once you see how carefully each side has done its work. The first way looks at the early universe. Remember the cosmic microwave background, the oldest light, the afterglow from 380,000 years after the beginning. Hidden in the faint temperature patterns of that ancient light is a wealth of information about what the universe was made of and how it was behaving in its infancy. By measuring those patterns with exquisite precision, using missions like the Planck satellite, cosmologists can work out, from the physics of the early universe, how fast it should be expanding today. It is a bit like studying a photograph of a child, and, from careful measurements of the photograph, plus a thorough understanding of how children grow, predicting exactly how tall the adult should now be. This early universe method gives a Hubble constant of about 67 kilometers per second per megaparsec. The units are not important tonight. The number is about 67. The second way looks at the nearby present-day universe and measures the expansion directly. Astronomers find galaxies whose distances they can determine very accurately using reliable cosmic mileposts, particular kinds of pulsating stars called Cepheids, and particular kinds of stellar explosions called type Ia supernovae. both of which have known true brightnesses and therefore reveal their distances by how dim they appear. By combining how far away these galaxies are with how fast they are receding, astronomers measure the expansion rate directly, here and now, without relying on the early universe at all. This is the work of a long-running project called SHEJUES, led by the astronomer Adam Rees and his colleagues, including Dan Skolnick, and the local method gives a different answer, around 73. And in a January 2025 result, using fresh data, the local measurement came in even higher, around 76.5. So there it is, 67 from the early universe, 73 and rising from the local one. Two numbers that should be the same, because there is only one universe and only one rate at which it is expanding. Two careful methods, each refined over decades, each cross-checked and stress-tested, and they will not agree. For a while, the comfortable assumption was that one side simply had a mistake somewhere, an unaccounted for error in the mileposts, a subtle miscalibration that would eventually be found and would bring the two numbers together. That is the normal way such things resolve. But as both methods have been refined, the error bars, the ranges of uncertainty around each measurement, have shrunk. And as they shrank, the two numbers did not drift toward each other. They held their ground, further apart than their shrinking uncertainties could explain. The disagreement has now crossed the 5 sigma threshold, the same gold standard we met with the Big Ring and the Higgs boson. In plain terms, the gap is now too large and too well measured to be a fluke or a simple mistake. It is, increasingly, looking like a real feature of the universe that the standard model does not capture. And the easy escape routes have been closing. In late 2025, the Atacama Cosmology Telescope, another instrument that maps the ancient microwave light, released its final data, an independent and very precise look at the early universe side of the measurement. It confirmed the early universe value, around 67, with great confidence, and in doing so, ruled out many of the simplest ideas that might have explained away the gap. If you had hoped the early universe number was slightly off, this made that hope harder to hold. The early side is solid, the local side is solid, and they disagree. Now, what does this have to do with arcs and rings and early galaxies? On its own, perhaps nothing. The Hubble tension could be a separate puzzle entirely, a sign that there is some ingredient missing from our recipe for the universe. Perhaps something about dark energy, the mysterious thing driving the expansion, that changes over time in a way the standard model does not allow. We will come to that possibility soon. But it is one more place where the model at the center of cosmology, the one built on the smooth, even, well-behaved universe, is being gently stretched. One more careful measurement that does not quite fit. Let us hold the calm here, because this is exactly the kind of place a tired mind can start to feel uneasy, and there is no need. Two clocks running at slightly different speeds is not the end of time. It is a clue. It is the universe telling us that our understanding is incomplete in some specific, measurable way, and incompleteness is not failure. It is the ordinary condition of science, the open edge where the next understanding will come from. The two clocks disagree. That is not frightening. That is interesting. And the people studying it are not panicking. They are measuring carefully the exact size of their own ignorance, which is the most honest thing a scientist can do. There is one more strain to meet before we turn to the explanations, and it is perhaps the strangest of all, because it touches the very heart of the assumption we began with. The cosmological principle says the universe has no preferred direction, no grain, no arrow, whichever way you turn, the same view. And several independent surveys of the sky have begun to suggest, softly but persistently, that this might not be quite true, that the universe might, after all, have a direction. This is the strangest of the strains, because it touches the deepest part of the assumption we began with 3 centuries ago. Isotropy, the idea that the universe looks the same in every direction. No grain, no preferred way to face, no arrow. It is the half of the cosmological principle that feels most obviously true, because what would it even mean for the universe to have a direction? And yet several independent surveys have begun to whisper that it might. Let us approach it gently, starting with the oldest light again, because the first hints are very old and very subtle. We have praised the cosmic microwave background for its remarkable smoothness, the same temperature in every direction to better than 1 part in 100,000. That smoothness is real, and it is the strongest evidence for isotropy we have. But when cosmologists looked at the tiny remaining variations, the faint patterns in that ancient light, they noticed a few oddities that have never quite gone away. One is a gentle lopsidedness, where one half of the sky seems to have slightly more variation than the other, called the hemispherical asymmetry. Another is a strange alignment of the largest patterns in the microwave sky. Patterns that, by the rules, should be oriented randomly, but which instead seem to line up with one another along a particular axis. Some cosmologists, half in jest and half in unease, gave that alignment a memorable nickname. They called it the axis of evil, not because there is anything evil about it, but because a preferred axis in a universe that should have none felt like a small affront to everything they believed. These microwave background anomalies are subtle, and on their own, many cosmologists were comfortable filing them away as statistical flukes, the kind of mild oddity you expect to find somewhere when you examine a rich dataset closely enough. One faint alignment in the ancient light is not enough to overturn isotropy, but the microwave background is not the only place a direction has shown up. The stronger hints come from counting things across the sky, and here we need one piece of background gently to understand why the counting matters. We know that our own galaxy is moving through the universe. The Milky Way, carrying us with it, drifts through space at a few hundred kilometers per second, and that motion should produce a small, predictable effect when we count distant objects across the sky. Because we are moving in a particular direction, objects in the direction we are heading should appear very slightly more crowded and slightly brighter, while objects in the direction we are leaving should appear slightly sparser. It is a gentle cousin of the way headlights seem to bunch up ahead of you as you drive down a road at night. This expected lopsidedness, caused purely by our own motion, is called the kinematic dipole, and cosmologists know how large it should be because they can measure our speed independently from the microwave background. So here is the test, and it is a clean one. Count enormous numbers of distant objects across the whole sky. Subtract the lopsidedness we expect from our own motion, and whatever is left over should be nothing. A smooth and even distribution, because the universe beyond our local motion is supposed to be isotropic, the same in every direction. That is the prediction. After accounting for our own movement, the deep universe should look perfectly balanced. It does not look perfectly balanced. This is the heart of the matter. Survey after survey, using completely different kinds of objects, has found that after you subtract our own motion, there is still an excess in roughly the same direction, a residual lopsidedness larger than our motion can explain. One survey counted distant radio galaxies. Another, called Catwise, counted around 1.6 million quasars selected by their infrared light. Others counted optical galaxies and yet more quasars. And across these independent surveys, looking at different objects with different instruments, a consistent extra dipole keeps appearing, pointing in broadly the same direction, and it is roughly twice as large as the motion of our galaxy should produce. The work most associated with this puzzle comes from the astronomer Nathan Sechrest and his colleagues, who have studied the quasar dipole carefully across several years. And when the various measurements are considered together, the combined significance of this anomalous direction, this apparent preferred axis that should not exist, climbs above 5 sigma. Once again, that gold standard threshold. The excess is, by the numbers, too consistent and too large to be easily waved away as chance. Now, here is where the careful balance matters, because this result is genuinely contested, and the honest thing is to hold it lightly. There are real, sober reasons a residual dipole could appear without overturning isotropy. The objects being counted are not perfectly uniform across the sky. Quasars vary in brightness. Surveys have subtle differences in how completely they cover different patches. And there could be effects in how these distant objects evolve that mimic a direction without there being one. The dust of our own galaxy gets in the way along certain lines of sight. These are exactly the kinds of subtle systematic effects that careful astronomers worry about. And some researchers have argued, in reassessments of the same data, that the dipole may be smaller or partly an artifact once these effects are fully accounted for. The measured significance has ranged across different analyses, from a milder couple of sigma up to the full 5 and beyond, which tells you the question is still genuinely open. This is not settled science. It is a live and ongoing conversation with thoughtful people on more than one side. And yet, like the Great Wall sharpening with more data, the dipole has been stubborn. It keeps showing up in different objects, across different surveys, pointing the same way. That persistence is what keeps it on the table. A single survey finding a direction could be its own quirk. Several independent surveys finding broadly the same direction is harder to dismiss. And there is one more idea, raised in recent years, that is worth ending this section on, because it gathers several of tonight's threads into a single quiet thought. Some researchers have begun to wonder whether the Hubble tension, the two clocks that disagree, and this apparent preferred direction might not be two separate puzzles at all, but one puzzle seen from two angles. The thought is this: if the universe is not quite as smooth and even as the cosmological principle assumes, if there is some genuine large-scale lopsidedness to it, then the expansion might appear to happen at slightly different rates in different directions, which could show up as the disagreement between our two clocks. In that picture, the oversized structures, the directional dipole, and the Hubble tension would all be different faces of the same underlying fact, that the universe has a little more large-scale structure and a little less perfect smoothness than we assumed. Several anomalies possibly becoming one. We have now gathered all the strains, the oversized structures across space, the early galaxies across time, the two clocks that will not agree, and the faint suggestion of a direction. The natural question, the one any curious mind arrives at by now, is simply, what could be going on? What kind of universe produces all of this? And the honest answer is that no one knows for certain, but there are ideas, real ones, physically motivated, ranging from the merely unexpected to the frankly wondrous. We will spend the next movement walking through them gently, not as answers, but as open possibilities, the working maybes of a field standing at a threshold. So that is where we go next, slowly and without any hurry. So what could be going on? We have gathered the strains, and now we walk through the leading ideas, with no rush to declare a winner, because the field itself has not declared one. These are working hypotheses, the maybes a careful science keeps on its table while the evidence comes in. Some of them are modest adjustments to what we already believe. One of them is genuinely strange and wonderful. Let us take them gently, from the most ordinary to the most extraordinary. The first possibility is the most conservative, and it concerns the mysterious thing driving the expansion of the universe, the thing we call dark energy. For decades, the Standard Model has treated dark energy as a constant, an unchanging property of empty space itself, the same yesterday, today, and a billion years from now. That assumption is built right into the name of the Standard Model, which cosmologists call lambda-cold dark matter, where lambda is the symbol for that constant dark energy. But what if it is not constant? What if dark energy changes very slowly over the long ages of the universe? This is not idle speculation. In 2025, a vast survey called DESI, which is measuring the positions of millions of galaxies to map the history of cosmic expansion in detail, released results that contained a gentle hint. The data suggested, though did not yet prove, that dark energy might have been slightly stronger in the past and slightly weaker now. A dark energy that evolves rather than holds perfectly still. If that hint holds up as more data comes in, it would be a genuine revision to the Standard Model, and it could ease the Hubble tension, because a changing dark energy would naturally produce a slightly different expansion history than a constant one. This is the most down-to-earth of the explanations, a single ingredient in the recipe behaving a little differently than we assumed. It would not be a revolution. It would be a correction, the kind science makes all the time. The second possibility reaches back to the very beginning, to those faint early ripples we spoke of, the variations smaller than 1 part in 100,000. The Standard Model assumes those ripples were random and even, with no preferred scale and no preferred direction, scattered through the infant universe like perfectly fair static. But what if they were not perfectly random? What if the initial conditions of the universe carried some faint pattern, some preferred scale or gentle direction, built in from the first instance? A slightly non-random set of starting ripples could, over billions of years of gravitational growth, blossom into exactly the kind of oversized, organized structures and gentle preferred direction we seem to be finding. In this picture, the strangeness we see today was seeded at the very beginning, written into the universe's first breath. And then there is the third idea, the one that sounds like science fiction and is, in fact, serious theoretical physics. Cosmic strings. To understand cosmic strings, we have to go back to the first fraction of the first second after the Big Bang, when the universe was unimaginably hot and changing fast. As the young universe expanded and cooled, it passed through a series of transitions, a bit like the way water passes from steam to liquid to ice as it cools. Each transition a sudden reorganization of how matter and energy behave. Physicists call these phase transitions, and they happened when the universe was unthinkably young and hot. And there is a deep idea in physics, worked out in the 1970s by the physicist Tom Kibble and developed by many since, that says these early transitions could have left behind flaws, defects, places where the reorganization did not complete smoothly, frozen into the structure of space itself, the way ice freezing across a pond can trap cracks and seams as it sets. A cosmic string would be one kind of such defect, a one-dimensional flaw, a line, and it would be extraordinary. Thinner than a proton, far thinner than an atom, thinner than almost anything you could name, and yet enormously, almost incomprehensibly massive, because it is made not of matter but of trapped energy from that early transition, wound into a thread of pure tension. A single stretch of cosmic string the length of a small mountain could outweigh the entire Earth. These strings, if they exist, would stretch across vast reaches of space, some of them spanning the observable universe, others curled into great loops, all of them carrying immense gravity along their impossibly thin lengths. And here is why they matter for tonight's story. A cosmic string's gravity would not pull matter into a sphere the way an ordinary clump of mass does. It would pull matter toward a line. Galaxies and gas drifting near a cosmic string would be drawn along its length, gathering into long, thin, curved arrangements, into arcs, into walls, into rings where a loop of string once passed. The very shapes that seem too large and too organized to have formed by ordinary gravity, the arc, the ring, the wall, are close to the shapes that the gravity of a cosmic string would naturally produce. A defect left over from the first instant of the universe, seeding the great curved structures we find billions of years later. It is a genuinely elegant idea. But we must be careful and fair, and the honesty here is the most important part. Cosmic strings are hypothetical. We have never detected one. They are predicted by certain theories of the early universe, and they are entirely consistent with known physics, but they remain unconfirmed, a possibility rather than an observation. The foundational work on their physics, gathered in reviews and textbooks by physicists like Vilenkin and Szilard building on Kibble's original insight, lays out carefully what they would be and how they might reveal themselves, and the search for them is real and ongoing. But no one has found one yet. To say that cosmic strings explain the giant arc would be to get far ahead of the evidence. The honest statement is gentler and more interesting. If cosmic strings exist, they would naturally produce the kinds of shapes we are puzzling over, which makes them one of the most appealing of the working maybes, and a real reason to keep looking. So those are three of the leading ideas. A dark energy that quietly changes, initial conditions that were not perfectly random, and cosmic strings, threads of frozen tension from the first instant, sculpting the great, curved structures. Notice what they have in common. None of them breaks physics. Every one of them is built from physics we already know or seriously theorize. They do not tear down the cathedral of cosmology. They renovate a room or two, or add a wing no one had thought to build. That is what these anomalies most likely call for. Not demolition, revision. And yet there is one more idea further out than any of these, gentler and stranger and more philosophical, that stretches the very concept of time and asks whether our universe might be only the latest in an endless series. It is a minority view, held by few, contested by most, and it is one of the most beautiful thoughts in modern cosmology, a good place to slow all the way down. It comes from one of the great minds of physics, and it imagines the cosmos not as a single event, but as a breath in an endless cycle of breaths. We come now to the gentlest and strangest idea of all, and it asks us to slow down, because it leaves the structures and the measurements behind entirely, and turns instead to time itself, and to whether our universe is the only one there has ever been. The idea belongs to Roger Penrose, one of the most distinguished physicists of the last century, a man who shared in the deepest discoveries about black holes and the structure of space-time, and who, late in his career, turned his attention to a question most cosmologists set aside. What came before the Big Bang? The standard answer is that the question has no meaning. That time itself began at the Big Bang, and asking what came before is like asking what lies north of the North Pole. But Penrose was not satisfied with that, and he proposed something remarkable. He called it conformal cyclic cosmology. The idea, told softly, goes like this. Our universe is expanding, and as it expands, it grows colder and emptier and more spread out. Stars will eventually burn out. Galaxies will drift apart. Even the black holes, the longest-lived things in the cosmos, will, over almost unthinkable stretches of time, slowly evaporate away into faint radiation, until at last the universe is nothing but a thin, cold, featureless bath of light, spread across an infinity of space, with no matter left to mark distance or time at all. And here is where Penrose makes his strange and beautiful leap. He argues that a universe in that final state, empty and cold and full only of formless light, is, in a deep mathematical sense, indistinguishable from a universe in its very first instant, hot and dense, and also full of formless energy, before any structure existed. The end of everything and the beginning of everything, he suggests, share the same essential geometry. They are the same kind of thing, and so the cold, empty end of our universe could become the hot, dense beginning of the next one. The death of one cosmos seeding the birth of another, not once, but endlessly, in a chain of universes stretching infinitely into the past and infinitely into the future. Each cycle he calls an aeon. Our universe is one aeon in a sequence with no beginning and no end. It is, taken purely as an idea, one of the most expansive thoughts a human being has ever offered. Not a universe, but an endless succession of universes, each one rising from the ashes of the last, each one a single breath in a rhythm that has always been breathing and always will be. Whether or not it is true, it stretches the mind in the gentlest possible way, the way the night sky does, by making our own enormous universe feel like one quiet chapter in something even larger. And Penrose did not leave it as pure philosophy. He suggested it might leave a trace, a way to test it. If aeons truly follow one another, then violent events in the previous universe, particularly the collisions and mergers of enormous black holes near its end, might leave faint imprints carried across the boundary into the next one. In our universe, those imprints would appear as faint, nearly circular rings in the cosmic microwave background, gentle ripples in the oldest light, the fading echoes of events from a universe that existed before our own. Penrose and his collaborators have claimed to find hints of such rings in the microwave sky, and they named the suspected sources Hawking points, after Stephen Hawking, whose work on evaporating black holes is woven into the idea. Now, the honesty here matters more than anywhere else in tonight's story, so let us be very clear and very gentle about it. Conformal cyclic cosmology is a minority view. It is held by few cosmologists, and it is contested by most. The claimed rings in the microwave background have been disputed, with other researchers arguing that patterns like them can appear by chance in the ordinary random fluctuations of the ancient light. The same careful pattern in noise worry we have met again and again tonight. The mainstream of cosmology does not accept conformal cyclic cosmology as established, and it would be wrong to suggest otherwise. And its connection to the Big Ring, the structure in our title, is thematic rather than direct. Penrose's rings are imprints in the oldest light, not arrangements of galaxies, and no one is claiming the Big Ring is a Hawking point. The resonance between them is poetic, a rhyme of shapes, not a proven link. So why include it at all if it is so far from consensus? Because it makes a gentle point that is worth carrying into sleep, regardless of whether the specific theory is right. The point is simply this: the cosmos may hold a history far deeper than our models assume. We tend to treat the Big Bang as the beginning of all things, the first page of the only book. Penrose's idea, whether true or not, reminds us that this assumption too is a choice, a frame we have placed around our understanding, and that the real cosmos is under no obligation to respect the edges of our frames. There may be more time, more universe, more story than we have yet imagined, and there is something profoundly restful in that thought, the sense of being held within something vast and old and patient, something that was breathing long before us and will be breathing long after. We have now walked through all of it, the rule and why it felt so safe, the oversized structures across space, the arc and the ring and the wall, the early universe Webb revealed, grown up too fast, the two clocks that disagree, and the faint suggestion of a direction, and the candidate explanations, from a changing dark energy to threads of cosmic string to an endless cycle of universes. It is a great deal to hold, and you do not need to hold all of it. The threads matter less than the shape they make together. So in the last part of tonight's story, we will gather it all into a single quiet picture and ask the one honest question the whole field is now circling. Not with alarm, just with the calm curiosity that has carried us this far. And then we will bring the lights all the way down. That is where we drift for the last time. Let us step all the way back now and simply count. For most of tonight, we have looked at these anomalies one at a time, the way they were found, scattered across years and methods and teams. But the real weight of them is only felt when you set them side by side and see how many there are. Start with the Hercules Corona Borealis Great Wall, found in 2014, traced through the deaths of giant stars, possibly 10 billion light-years across. That is one. Then the giant arc found by Alexia Lopez in 2021, traced through the magnesium fingerprints in quasar light, 3.3 billion light-years long. That is two. Then the Big Ring, announced in 2024, in the same patch of sky, 1.3 billion light-years across, shaped like a corkscrew that no familiar process is known to make. That is three. Then the proposed giant ring on the sky, the 2026 suggestion that the arc and the ring may be parts of a single larger system, a structure even greater than either alone. That is four, and these are not the first. Before any of them, astronomers had already found the Sloan Great Wall, an enormous sheet of galaxies stretching over 1 billion light-years, and the large quasar groups, sprawling associations of bright galactic cores that themselves pressed against the size limit when they were found. Add those, and you are somewhere around 7 structures found over roughly a decade and more by different teams using different methods, looking at different objects in different parts of the sky at different distances. And here is the gentle logic that makes the accumulation matter. Think about what randomness actually looks like. If each of these structures were a fluke, a rare chance alignment that beat long odds, then they should be scattered unevenly, appearing here and there in no particular pattern, each one an isolated accident unconnected to the others. That is how flukes behave. They do not coordinate. They do not accumulate in a single direction. But what we have instead is a steady drumbeat of oversized structures, found again and again by independent methods, all pointing the same way, toward a universe with more large-scale organization than the smooth model allows. One fluke is a fluke. 7, found by 7 different roads, begins to look less like a series of accidents and more like a pattern the universe is quietly insisting upon. And remember, the structures are only part of it. set them beside everything else we have gathered. The early universe Webb revealed, with its two massive, too mature galaxies, the big wheel spinning calmly where there should have been chaos. MOMZ 14, rich with chemistry it should not yet have. The two clocks of the Hubble tension refusing across 5 sigma to agree. The faint but stubborn suggestion of a preferred direction showing up in survey after survey. None of these, on its own, would overturn anything. Each has its careful skeptics, its possible mundane explanations, its honest uncertainties, and we have given those their fair hearing all night long. But they are all leaning gently in the same direction. They are all whispering the same soft thing, that the universe is a little less smooth, a little more structured, a little stranger and larger than the assumption at the center of our cosmology supposed. When the astronomer Robert Massey of the Royal Astronomical Society was asked about the Big Ring, he did not call it a crisis or a revolution. He called it simply food for thought. And that phrase is just about perfect for where the field actually stands. Not at an answer, not at a catastrophe, at a table with a great deal to think about, and the humility to admit that the thinking is not finished. And so we arrive at the question, the one Alexia Lopez herself raised, plainly, to her entire field, after she had found a second impossible shape in the same patch of sky. She did not phrase it as an accusation or a triumph. She phrased it as a careful person genuinely asking, do we need a new standard model? Do we need to revise the assumption that has held for 300 years? Is the cosmological principle, the smooth and even universe, the floor under every equation, still the right floor to stand on? Or is the universe telling us, gently and from several directions at once, that it is built on something a little different than we thought? It is worth being clear about what that question does and does not mean, because the title of tonight's story uses the words breaks physics, and we promised at the very beginning to be honest about them. Nothing here breaks physics. The laws that govern atoms and light and gravity are exactly as they were. What is being questioned is not physics itself, but one particular assumption within our model of the universe, the assumption of perfect large-scale smoothness, and the standard model built upon it. To break the cosmological principle would not be to break the universe. It would be to discover that the universe is organized a little differently than our simplest, most beautiful assumption allowed. That is not a catastrophe. That is a correction. And correcting our maps is the oldest and most honorable work that science does. Maybe the answer to Lopez's question will turn out to be no. Maybe the skeptics are right, and with more data and more careful accounting, these anomalies will soften and settle, and the smooth universe will hold after all, vindicated once more, the way it has been so many times before. That is a real possibility, and an honest one, and the people who argue for it are doing good and necessary work. Or maybe the answer will be yes, and the next generation of cosmologists will grow up with a model that has a little more structure in it, a little more direction, a richer and stranger floor beneath the equations. We do not know yet. We are standing at the threshold, not past it, and there is no need to rush across. What we can say is that the universe has handed us a genuine, beautiful puzzle, the kind that comes along only rarely, and that the people working on it are doing so with care and honesty and an openness to being wrong that is the very best of what science can be. That is a good place to leave it, not resolved, just genuinely, wonderfully open. So let us bring it all the way down now, slowly, and end where these things should always end, which is with you, here, wherever you are, safe and still. Here is the first and most important thing to carry into sleep. None of what we talked about tonight changes anything about your life or your world or the ground beneath you, the Earth still turns on its axis, exactly as it has for 4.5 billion years. It still circles the sun once a year on the same gentle path. The sun still rises and sets. The seasons still turn. The atoms in your body still hold together the way they always have, bonded by the same forces, obeying the same laws, completely untouched by any question about the larger structures in the distant cosmos. If every word of tonight's anomalies turns out to be real, and the cosmological principle is revised, the tides will still come in. The moon will still light the garden. Your breath will still rise and fall. What might change is only our map, only the picture in our minds of how the larger scales of the universe are arranged. And a map is a precious thing, but it is not the land. When we redraw a map, the territory does not shift an inch. The mountains stay where they always were. We simply see them a little more clearly than before. And redrawing the map is not a failure. It is the whole story of science, the thing it has always done, the thing it is supposed to do. There was a time when we were certain the Earth sat at the center of everything, and the heavens turned around us. Then we learned that the Earth moves, that it is the sun we circle, that we are not the center after all. That correction was frightening to the people who lived through it. It overturned an assumption that had felt as safe and obvious as the ground. And in hindsight, it was not a loss. It was a gift. It made the universe larger and stranger and more wonderful than the small, tidy cosmos it replaced. It happened again with relativity, when we learned that space and time themselves bend and stretch, that they are not the fixed and absolute stage we had always assumed. It happened again with quantum mechanics, when we learned that the smallest pieces of the world behave in ways that defy every intuition we brought to them. Each of these was a revision that frightened its own time and freed every time after. Each one took an assumption that felt like solid floor and revealed it to be a single room in a much larger house. And every time, the universe that emerged was not smaller and colder for the correction. It was vaster and richer and more full of wonder than the one we had thought we lived in. So if the cosmological principle is bending, if the universe is turning out to have a little more structure, a little more direction, a little more strangeness than we assumed, then we are simply living through another one of these moments, another gentle widening of the house, and there is nothing to fear in it. There is, if anything, something to be quietly grateful for, that we happen to be alive at a time when the map is being redrawn, when a graduate student following the light of distant quasars can find a shape that makes an entire field lean forward and wonder. Here is the thought to fall asleep on. The universe is under no obligation to fit inside the box we built for it. It never agreed to our assumptions. It never promised to be smooth or even or simple, or to respect the limits we sketched around it. It simply is what it is, vast and old and patient, going about its business on scales of space and time we can barely hold in our minds. And every so often it lets us catch a glimpse of just how much larger than our ideas it really is. The arc, the ring, the wall, the early galaxies grown up too fast, the two clocks that will not agree, the faint direction in a cosmos that should have none. These are not the universe failing to make sense. They are the universe being honest with us, showing us, gently, that there is more to understand than we had thought. And that is the most restful thing of all. Not that we have the answers, but that we do not, and that the not knowing is not a darkness, but an open door. The mystery is not a problem to be anxious about. It is the very thing that makes looking up worthwhile. If we already understood everything, there would be nothing left to wonder at. The fact that the universe still has secrets, still has shapes too large to explain and questions too deep to close, is exactly what keeps the night sky worth lying beneath. There will always be more, and there is a deep and gentle comfort in that. So let the questions stay open tonight. You do not have to solve them. No one does, not yet, and maybe not for a long time, and that is perfectly all right. The astronomers will keep looking, carefully and honestly, the way they always have. The data will keep coming. The map will keep being drawn, and the stars above your roof will keep their places through all of it, exactly as they always have, asking nothing of you but that you rest beneath them. The universe is larger than the box we built for it. It is in no hurry to explain itself, and neither, tonight, are you. Let your breathing slow. Let the questions drift. Let tonight be soft. The cosmos will hold them all until morning.